Okay, hi kids. We're back for part 2 of the video 4.3, connecting f prime and f double prime with the shape of the graph of f. So we're on example 4 where it says the graph of f prime, the derivative of a function f on the interval from -4 to 4 is shown in the graph below. Answer the following questions about f. Justify each answer with information obtained from the graph of f prime. First, it says, on what intervals is f increasing or decreasing? So you have to remember that if we're going to justify our answer, we have to answer it substantially, not just with on this given interval. So now if I look at this, I could do a chart for this, but I've already highlighted in the graph. I'm looking at the graph of f prime. So I'm going to mark this up a little bit where I can see that f prime is greater than 0 here. And there's a point where it looks like f prime is equal to 0, and that's at 2 right here. And then again, f prime is greater than 0. And then at 1, f prime is equal to 0. And then down here, it looks like f prime is less than 0 on that interval. So f is increasing on the interval. Remember, we're on a closed interval. So that's going to be increasing. Then we're talking about from, let's go down to decreasing first. I'm going to go left to right. So it looks like decreasing and increasing. Oops, here, wait a minute. Let me just do it. So we'll start at the first one. F is increasing then when f prime, keep in mind, when f prime is greater than 0. So that occurs on the interval from -4. We're going to start at -4. Put a comma, so -4, and then it's going to go to -2. And then I guess I'm going to make it just brackets there. It's not really going to matter, as I've spoken to you about this before. Union, and then I'm going to pick it up at -2. Still, f prime is increasing because it's greater than 0. And then it's going to go to 1. Okay, so then f is decreasing when we get to 1. F is decreasing when we get to 1, and we go to 4. And those are the intervals. Okay, so I could do an entire chart of this so that I could show you, but the justification where f is increasing is when f prime is greater than 0, and it's decreasing when f prime is less than 0, and I have the graph color-coded. I found that that often helps out tremendously when you're trying to decide when we're looking at the graph of f prime. Now, on what intervals is the graph of f concave up or concave down? So if I'm looking at this graph, I'm going to say, well, it's concave up when f prime is increasing. I'm going to abbreviate a little bit here. And it's concave down when f prime is decreasing. So that's kind of easy to see. So if I use my colors here, let me be careful about how I use these. So when f prime, the graph, is increasing, think about what this looks like. That would be I got to be careful how I color this. I don't want it to be too fat of a line or a curve here. So let's do this. F prime increasing here, right? It seems to get to a maximum point. Let's say that's going to be about 0 there. Okay. And it looks like it's increasing here too, right? Now it looks like it's decreasing when we go here. F prime is decreasing here. And it also looks to be decreasing here, right? So with the green, f prime is decreasing. So it looks like we have places where f prime is equal to 0 that are kind of telling us something. Here, let's get some orange. See here, here, and here, right? So the graph turns out to be concave up from -2 to 0. -2 to 0, and I'm going to use, now we're talking about something a little bit different, so we're not talking about increasing and decreasing, so I'm going to be careful with the use of the brackets here. Then it looks like, and what are we being asked? On what intervals is the graph of f concave up and concave down? So if I look from 3 to 4, then that's where f prime is increasing. Okay, now you got to be careful. We're looking at the graph of f prime. So where the graph is increasing, that's where the graph where the graph of f prime is increasing, the graph of f is concave down. Now let's look at f being concave down. Let me digress just a second. Where the graph of f is concave up, f prime is increasing. Now I'm going to look where f is concave down, and that will be where f prime is decreasing. So I'm going to start at -4, and I'm then going to go to -2, and then union, I'm going to pick up at 0, and then I'm going to go to 3. Okay, so then we have at which x coordinates does f have local extrema? That's when there's a sign change that occurs in f prime. Remember where it goes from a positive to a negative at a critical point, f prime, where f prime goes from a negative to a positive, you have extrema. Now in this first case, you have extrema that is a max, right? And here you have the case where you have a min. Okay, so let's see what happens. So it looks like at -2, do you see where the blue is? Okay, it looks like there's a sign change. There could be a possible sign change, but if you notice, it goes from f prime is greater than 0 to f prime equal to 0 to f prime greater than 0. So remember, we don't have a sign change in f prime there. We do have a critical number, but no sign change in f prime. So we don't have anything at -2. We don't have extrema at -2, sorry. But then if you notice at 1, at x equal to 1, what do we have? We have f prime is greater than 0. Here, let's zoom in. We have f prime is greater than 0 to the left of 1. And then we have f prime is less than 0 to the right of 1, right? So there's something happening by the first derivative test. There's a local maximum. So this means at 1, there's a local max. Okay, a local maximum. But, and then if you look, because the function increases from the left endpoint and decreases to the right endpoint, there are local minima at the endpoints. So let's look at this again. So if we have, so at x is equal to, I'm going to let you guys check this out and answer questions about this. It turns out we have local minima at x is equal to -4 and 4. Now, we don't have a graph of this. So here we have a local minima at -4 and 4 in addition to the local max at 1. So, yeah, I guess we should probably say that local minima and local maxima here at x is equal to 1. And that would be all of the local extrema. Okay. And I hope you can see at the end point, because where you have the function is decreasing, let's check back with this tomorrow. I don't want to make this video too long for this example, but we'll talk more about that. All right, and then you have what are the x-coordinates of all inflection points of the graph. It's where f double prime is equal to 0, and f prime goes from increasing to decreasing or decreasing to increasing. Now, so if you're looking at the graph at -2, what happens? It looks like f prime goes from decreasing to increasing. So it looks like f double prime is equal to 0. By the concavity test, you have it goes from the graph is concave up, but that means that f prime on this side is positive and f prime is positive over here, right? But at the same time, f prime is increasing. So it goes from f prime increasing to f prime increasing, so nothing's going to happen at -2, right? So the inflection points in the graph is where f double prime and f goes from increasing to decreasing. These are points of inflection, right? So if you look, f prime is decreasing, and f prime is increasing. So at that point, -2 is a POI. And you can see it's where this is happening as well. F double prime is equal to 0. Okay, let's look at the next point. So if you're at 0, you can see up in the graph up here, at 0, this point, and then we have at 3, you can see you have those horizontal tangents where f double prime in orange, let me write that, because the slope of the slope graph here, you can see f double prime is equal to 0 here. F double prime is equal to 0, even though it's at a place where f prime is equal to 0 on the x-intercept. And then down here, f double prime, the slope of the f prime graph is also equal to 0. So those are the 3 points we're looking at here. So you can kind of see at 0, let me get green again, we have f prime is increasing. I'm going to use an I. And then f prime is decreasing. So we also know that f double prime is equal to 0 there. So then that means we have another POI here at x is equal to 0. So now we have 2 POIs, 2 points of inflection, one at -2, one at 0. And then you have another one at 3, where if you're looking at the graph and you're going, well, f prime is decreasing and f prime goes to increasing, then that means since f double prime is equal to 0 at 3, then we know that we also have a point of inflection here at 3. So the 3 points of inflection, the points are at x is equal to -2, 0, and 3. And you kind of confirm that with the original graph up there, okay? Now, I sketched a possible graph lining up all the information down below where the graph goes from increasing at -2, and then at 1 it goes to decreasing. And then the concavity about -2, concave down, concave up, and then you get to 0, it goes to concave down, and then at 3 it goes to concave up. So that's kind of what a possible graph could look like. I'll focus on the word possible graph because I'm looking at the concavity, the points of inflection. I think I have them all labeled right. Yeah, where you have an absolute max, okay, and the local and the absolute max up there at 1. So here's at x is equal to 1 here. Okay, so that problem was a lot of thinking in terms of addressing issues that occur with a graph, looking at the graph of f prime and saying f prime is greater than 0, less than 0. What does it mean for the original function? Same thing with concavity, concave up, concave down. Okay, now I want to see if I can get one more problem done here. This is particle motion. So with particle motion, a particle is moving along the x-axis with the position function given of x of t. So when you look at this, we have x of t, and we have the units on the graph, and you can kind of figure out what the units are if you're looking at the function itself. When x is 0, what do I get there? And so you can kind of see you're at this point, so it looks like those units are in terms of 5, 10, 15, so on. And then the units as you go left to right are the number of seconds, and you can generally tell what they are, and each of these graphs are going to be very similar with that. So we start off and we take the original function, and we can note some things about it. So you can see at 1, you've got this, what we would call a local max here on x of t, right? And you have also a local min of x of t. And then we can kind of see that the derivatives are, the derivative x prime of t would be equal to 0 at those 2 points. So with that, then we can also see that the graph of x of t goes concave down first till about 2. So this looks like a possible POI, point of inflection, and we'll verify that with the information from all of that, with the information from the velocity and then the acceleration as we go forward, okay? So you have the position graph, x of t, and you can see that as it ends, it's going up to infinity. I'm going to see that it starts off at that 0, 5 point. Okay, so we've kind of marked up the function. So our information in the derivative graphs should match with that. Okay, we're going to go to v of t. So since we have v of t is x prime of t, then what I'm going to do with this one is I'm going to pull out a common factor of 2, and then I'm going to factor it as t minus 1, and then 3t minus 11. I kind of skipped a step in there. So you can kind of see that the critical numbers, then, the critical numbers of this are going to be t is equal to 1 and 11 thirds. So put the 1 there. 11 thirds is 3 and 2 thirds. So 11 thirds. Okay, in this case, we want to find the velocity, and we don't have, do we have units here? I don't think we have units on the time, right? So picture them being seconds, I guess, if you want to, if it helps you. Okay, so we're going to take this function, and I'm just going to use, I'm going to leave the 2 here because I think sometimes people wonder what happened with the 2. The 2 is positive, so it's not going to affect the sign of the derivative here. So then I'm going to put a, if I'm going to put a critical, or I mean a test point in here, I'm going to put that in. I'm going to put 2 here, and then I'm going to put 4 over here. So on the interval. So dividing the number line into critical numbers, into 3 regions to test, I'm going to put in 0.5 into t minus 1, 0.5 minus 1. So I'm going to put these test points into the derivative. And so I get 0.5 minus 1, which is negative. And 3 times 0.5 minus 11 is also negative. So it looks like we get a positive derivative here. So then we get a positive derivative. That means the behavior of x. So let's talk about x down here, where up top we have the sign. So that means x is increasing at that point. I could just abbreviate that. It'll save a little bit of time here. So x is then increasing. Remember, that's your position function. And I need to scooch this one down just a little bit here. Okay, and then go to make a statement about that. Which way am I moving? If velocity is positive and it's a particle moving left, right on a line, we're going to say the movement, the particle, right underneath that. Probably a little sloppy. It could be neater. Particle motion. Let's see. Particle motion. I would say that we're moving to the right then. Okay, or the particle is moving to the right. So then I'm going to put in the test point of 2. So I get 2 minus 1, which is positive. And 3 times 2 minus 11 is still going to be negative. So we have a negative derivative. So x then, in this way, here, x is then going to a decreasing. X is decreasing. And then that means that we're going to look at the particle moving to the left on that interval from 1 to 11 thirds. We're going to then put 4 in to the factored form. 4 minus 1 is positive, and 3 times 4 minus 11 is still going to be positive. So we have x prime is going to be positive. That means x is then increasing in the interval from 11 thirds to infinity. And that means the particle is moving to the right. Okay, so we analyze that for the particle motion. Okay. And then we get to a of t. So a of t is 12t minus 28. So I'm going to pull out a factor of 4, right? And that leaves me with 3t minus 7. So I'm going to look at the critical numbers as, I hate to use critical numbers with this because it's really not, but I'm going to call them the zeros of the second derivative. So possible POIs, I guess I like to call them because you recognize it, but this is acceleration. So I'm going to set that equal to 0, but I'm going to say those are then t is equal to 7/3. So I'm going to put that on the number line, and we're going to test for the sign of the second derivative. So I'm going to put test points in here. So 7/3 is 2 1/3, so I can put a 1 here, and then I'll put a 3 on this side. So then with the test points, testing the sign of the acceleration, the second derivative. So it looks like if I just have one factor, right? So it's up with the 4 out front, and then here, and then the 4, and then the 3. So if I put a 1 in for t, I get a 3 minus 7, which is negative. So that means the sign of x double prime is going to be negative. And then we put a 3 in, and we have 3 times 3 is 9 minus 7, which is positive. So then the sign is positive on the interval from 7/3 to infinity. So I have those two, negative to a positive, about 7/3. And so let's look at the graph first. If we're looking at the graph of x, and I guess I said this, I was really talking about the graph up here being increasing. So if I say the graph of x, so it looks like the graph would be concave down on the left of 7/3. To the right of 7/3, the graph would be concave up. Okay, I hope everybody's all right with that notation then. And then the particle motion then would be decelerating. And then on the left of 7/3, it would be accelerating to the right of 7/3. So in this case, we found the velocity, the acceleration, and we described the motion of the particle. So we could put this together in one, and you can kind of see where here you have x double prime is less than 0, and we'll talk some more about this tomorrow. X double prime is greater than 0. So you can see right here is where x double prime is equal to 0. Okay, and the same thing when we were evaluating the graph of x prime, where x prime is greater than 0 at these two places. And then you have x prime is less than 0 on that red portion of the graph, which matches along with our number line here from 1 to 11/3 here. And then, of course, you have the blue portions on the outs from 0 to 1, and then from 11/3. If you look here, from 7/3 to infinity, x double prime is greater than 0. And then from 0 to 7/3, x double prime is less than 0. So just one more aspect of evaluating the graph. You can see that our answers here match up perfectly with what we have in the original graph of x of t. Okay, so now the next problem that we'll be looking at is the second derivative test for local extrema. And I'm going to start this one, but I think what I'm going to do is finish this one, and then that'll be it for the video tonight. So I really like this particular test because with this test, it's great when you have A, you have critical numbers, and then B, you have the second derivative. Because what you can do is you just put the critical numbers into the second derivative. And you remember critical numbers is where f prime is equal to 0 or undefined. Well, if you have f prime is equal to 0, then you can certainly say, all right, well, I'll put the critical number in to the second derivative, and then it'll tell me if the graph has a local max or a local min. So the first step is you find the critical numbers. So you see I took the first derivative already, and I put it in factored form. So the critical numbers in this case, and they're the c values that we talked about, are going to be x is equal to 0 and 4. So we have the critical numbers. Then we're going to input the critical numbers into the second derivative to determine the sign of f double prime of the critical numbers. So since f double prime is 6x, then we're going to take 0 and 4. And we're going to say f double prime of 0 is equal to 0, and f double prime of 4 is 6 times 4, so it's 24. So now we make a conclusion here about what we know, and this is one of the things that I'm going to point out that is kind of annoying about the second derivative test. At x equals to 0, we cannot make a conclusion. So that occurs when the second derivative test f double prime is equal to 0. We can't make a conclusion about that. But at x equal 4, since f double prime of 4 equals 24 and greater than 0, here's what we can conclude. Now think about what a graph looks like when the second derivative is greater than 0. It's concave up, right? So then 4, f of 4, must be at the bottom of the U shape, or the concavity is concave up. You can make it a U shape, it's just a picture. So therefore we conclude a relative minimum. Okay, so we have one more, example 8, I think a couple more problems that we'll go through, but most of them are pretty quick here. So 2 more we'll touch on in class tomorrow. This is long enough for you to review, and then you'll have a couple more examples to complete your 4.3 homework in my math lab. So you guys have a great night, and I will see you tomorrow. We'll pick up with example 7 in class and move from 4.3 to 4.4. You guys have a great night. Thanks so much. Allenator out.